So, what do we call an object with a regularly repeating arrangement of its atoms? We call that a crystal. Number 2, what do we call the simplest and smallest arrangement of atoms that can be repeated to form a particular crystal? What are those building blocks called?
Atoms.
No, the blocks that we repeat.
Atoms.
Legos.
Now I know what your parents feel like. Disappointed.
I don't have it.
Guys, it's a unit cell. Remember, this is not actually what the unit cell looks like. Remember the sliced up ones we looked at?
Oh, the
Yeah.
ball of those?
Those are the unit cells.
Yeah, that makes sense. You should have told us that.
Number 3, what do we call a surface along which layers of atoms can slide?
Not plane.
Mm-hmm. What kind of plane?
Oh.
Continental plane.
Give me a
It's
synonym
something
for
with-
slide.
Slides. Something. I forgot the name.
Sorry, I don't know synonyms.
Slip planes.
Okay.
I see. That's what
Slip planes. So a slip plane is a surface along which layers of atoms can slide.
I do not know.
Hi, welcome to Material Science. We've only been talking about this for a week.
Oh, that's somebody walking me out.
Yeah.
Sorry, I haven't been here for the better part of the week.
I just showed up like that.
Shut up.
So, what I have here are some styrofoam balls that we're going to use for our atoms. And we're going to build these one at a time and talk about them. So, the first one, we're going to have
Oh, I hate that one.
What are you doing now?
Oh no, is this gonna be the entire class?
I can still hear you.
oh, there's noises that irritate you? Wonder what that feels like.
I know. Kinda sucks. Too bad I don't feel sympathy.
I don't know anything more annoying than those sounds.
I can think of one. I can know.
Okay, so what we have here.
Thought you
Okay.
when you died.
So what we have here. 2 layers of atoms. Yes?
Yes.
Maybe.
They're packed together. And when we put those layers together, you can see they stack right on top of one another. I guess I need to hold that down here.
Unit stuff.
Okay? That is technically not the unit cell. Remember, the unit cell, we have them sliced up. But this is simple cubic structure. Can you see that rather than being in the depressions of between the spheres like this, they're stacked right on top of each other? So we would call that an AAAA pattern, right? If I keep building this, the next layer will stack just like this. It's the same layer over and over again. Can you guys see that?
No.
They're not here. The spheres are not lining up. Jacob, I'm trying to help you.
Yeah, I am.
Okay? So the spheres don't line up here. They line up directly on top of one another. So that is simple cubic. So for if we go to letter A, we're not going to do this part. So letter A is simple cubic. Write this in on your sheet. How would you describe the packing of this?
It's a simple cube.
No, I apologize. I should clarify. When we're talking about packing, we're either going to say that it's tightly packed or loosely packed.
Oh, it's tight.
I would say this is.
Tightly.
This is loosely packed.
Oh.
Yeah.
And it only has a few slip planes. It does not have many slip planes.
Eight.
Do you remember the other day we talked about what's more important for workability? What wins out? Packing or slip planes?
Slip planes.
Slip planes, right? Because if it's tightly packed, it doesn't matter if it's tightly packed if you don't have slip planes to move around. No, I believe there's only 8.
Oh.
It's either 4 or 8. I can't remember off the top of my head. That's above our pay grade. We're not going to get into that. Okay?
Smart enough for that
Wait,
stuff.
so we don't answer?
We're not going to give a number of how many slip planes there are. We're just talking relative terms. There's few. There's not a lot.
Oh.
That's what that relative number means.
I think it's 12.
No, it's not 12.
Come on.
I know that. That one is, I believe.
Isn't a slip plane just each one that's touching each other?
No.
Oh, never mind then.
No, because like here, slip planes are like this. It doesn't have to deal with how the atoms are touching each other. It's how they can move.
Okay.
Okay.
I have
Yeah.
temperature IQ.
Does that make sense?
Yeah.
Okay. Any questions about simple cubic? Well, then let's move on to B. B is body-centered cubic. That's what we're going to build next. So it looks very similar to simple cubic, except now we're obviously not going to be able to see the bonds between the atoms. This is just so that we can space them out. So those bamboo sticks only represent the bonds. You can't actually see them. Let me make one more layer here.
Red lights blinking, but your camera's live again.
I know, it's up here. We're good. We're still recording. I'm not sure what happened before. The display turns off so it doesn't eat up as much battery. Okay. So here, with body-centered cubic, can you see these atoms are not touching in the layer where in simple cubic they were? Yeah? The reason is, now instead of an empty space in the middle here, we have another atom. So there's the cube, and in the center of that cube, there's a body, there's an atom there. Hence the name body-centered cubic. Okay? So for letter B, it's body-centered cubic. What's our abbreviation? BCC. So fill that in on your paper.
You have to write the whole thing out, or just write BCC?
Where it says name, put body-centered cubic. Where it says acronym, put BCC.
Oh.
We call this an ABAB pattern. Here's the A layer, right? It repeats. B would be this layer. Now, is that truly a single atom? No, really what we're having here is if we build this out, can you see that the layers would be like this?
Yeah.
It's just we're showing the single atom in that layer. But there would be another atom here, and another atom here, and then one up here, and we're building it out as we go. How would you describe this packing? Tight packed, loose packed? It's still fairly loose, right? There's gaps between the atoms. But this has a better number of slip planes. This has many slip planes. So, loosely packed, many slip planes. Are you with me so far? So you can see there is space, but look, if I put an atom here in simple cubic, do you see how that's not a cube now? Like this one? So that's why we have to space this out, is to fit that atom in there and still have it be a cube. Cool? So let's move on to face-centered cubic. That's letter C on the back. You can fill that in. What's our acronym here? FCC. Let me show you how we build this guy.
The back can be tight.
Give me 1 second. So we have a layer of atoms there. Our second layer, guys, if you look at this, can you see instead of being lined up, we turn it, and can you see that these, the second layer fits into the depressions between these atoms. So there's a space here, these atoms fit here. And then we have another layer like this. And there is our face-centered cubic. You can see on the face of this cube, there's an atom in the center. Look, is there space to fit an atom in the center of this cube? No. So it's only on the face that we have that center there. We actually refer to this, how would you label this? Like this simple cubic was AAAA layers, right? They were the same layers. We had AB, AB for body-centered cubic. What do you think this is?
ABA.
It looks like it would be ABA, but here's how it actually lines up. It's ABC. The reason is, if you turn the cube on its side, what we really have is, here's layer A, one atom here. Here's layer B. C is opposite of that. Can you see how we took the triangle and we turned it this way? And then here, can you see how A and A line up?
Yes.
And then when you turn it on its side, it's a cube. So it is ABC. Okay? Packing.
Tight.
Tightly packed. Slit planes.
No.
Many.
Oh.
Right? This is our highest workable. This is our highest workable material because it's tightly packed and we're allowing the slit planes to move because there's a lot of them. Any metal that you think of high workability, like copper, aluminum, those kinds of things, are going to be face-centered cubic. Is this all ringing a bell? I hope. Then let's move on to our last one. Hexagonal close packed. What's our acronym for hexagonal close packed? HCP. So this one we start a little different. We make our hexagon like so. Then our next layer is actually only 3 atoms. And can you see how this is set so it doesn't stack on top of atoms? There's depressions here between the spheres. It lines up there. There's the second layer, that's just the same as the bottom, and there's our hexagonal close packed. And you can see these atoms, right, would fill in these gaps here. Yes? And they continue out this way. Tightly packed or loosely packed? That's tightly packed. Even though it looks like there's spaces here, right, when we fit that atom in there, it's tightly packed. Okay? What about slit planes? Many or few?
Many.
This one only has a few. Remember, we had to rank this and body-centered cubic? And we said that even though body-centered cubic is gappier, it's more loosely packed. Because it has a lot of slip planes, it's more workable. This one is tightly packed, but it doesn't have enough slip planes. So even though it would be a smooth transition for those slip planes to move, if you don't have slip planes to move, it's not going to be workable. Yeah? Does that make sense? Do we have questions on this, folks? So this low workability one would be like titanium. Remember we gave the example of they use titanium for joint replacements? Like in your hip or your knee? Because we don't want a metal that's going to bend or change shape easily. And if it's highly workable, it will. So, this last question, this hypothesis question, why do you think we care so much about different crystal structures in material science? There's lots of answers here.
Understand their properties.
Okay, to understand their properties, which in turn means what?
Their makeup? I don't know.
Yeah, you're on the right track, guys. Why do we care about the properties?
We don't.
We do. Big time.
No, we
Oh,
don't.
ha 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 ha. What, but why?
It's for
Why is it important to know, if you're a material scientist, why is it important to know about the properties of the materials?
I don't know.
I don't know the word I'm looking for.
To understand it, I don't know.
But why? Why do we want to understand it?
I guess it is,
Well, I just gave the example of titanium being stiff, right? Not being workable.
for more uses?
We want to know what we can use it for. We want to be able to pick the right material for the right application, right? Why don't we want to make a plane out of cast iron?
Because it's too
Really?
It's brittle and it's heavy, right? That's not a good thing. So, one of the main reasons we want to know about crystal structure is crystal structure dictates properties, right? The behaviors or characteristics. And those properties determine what the material can be used for, or what it would be good at being used for. For instance, copper. What's a main use of copper?
Electricity.
Wiring, right? It's a pretty good conductor. It's easy to work with. Is it the best conductor of all metals?
No.
No.
Is it gold?
Gold's a great conductor. Why don't we wire our house with gold?
Freaking
Expensive.
It's expensive. Well, zinc is a really good electrical conductor too, but why don't we wire our houses with zinc?
I don't know that one. Is it
Not
toxic?
enough.
Has a really low melting point.
Uh-huh.
So every time you turn on your light switch, if there's enough resistance through there that it warms up enough, you'd melt all your wiring.
Oh, that's fun.
So you have to understand properties to find the best material for the application that you need it for. And those properties mainly are dictated by crystal structure. Make sense? See all that stuff we've been talking about? Now we're going to start making all the connections with it. So what questions do we have? None? You're all masters of this now. Okay.